Hello. Hi, myself Susobhan, the assistant professor of SBIST, and my department is Electronics and Communication Engineering. Today I am discussing the MOSFET of solid state devices. Okay. So these are the outcomes I have discussed over here. First one is the basic MOSFET. Second one is the different kind of operating mode of MOSFET. Then I also discussed about drain characteristics curve, transfer characteristics curve, MOS capacitor, band bending diagram, and CV plot, capacitor versus voltage plot. Now this is the basic constructions of N channel MOSFET and P channel MOSFET. MOSFET means metal oxide semiconductor field effect transistors. There are basically two types. One is N channel or the P type substrate, and second one is P channel when the substrate is N type. That means basically they are classified into two types. One is N channel, another one is P channel, and this is basically three terminal device. The first terminal is source, second one is gate, and third one is drain. So what is source terminal? This is one kind of BJT, bipolar junction transistors. There are some similarities matching with BJTs. BJTs are also three terminals device. They are emitter, base, and collector. Similarly, in case of MOSFET, these are basically source, gate, and drain. So what is source terminal? Source terminal is a terminal through which the majority carriers enter into the channel, okay, which is called a source terminal, and the conventional current entering the channel at S is designated by source terminal. This is the source terminal through which the majority carriers enters into the channel. In case of P type substrate, the majorities are holes. In case of N type, the majorities are electrons. Now the second terminal is drain terminal in both cases. So the terminal through which the majority carriers leave the channel is called drain terminal. Okay, this is the channel. This is the channel which is basically constructed in between two types of semiconductor bead. Suppose this is in this figure. I have chosen N type of bead, and the second figure I have chosen P type of bead. So this channel is N channel and this channel is P channel, because this channel is constructed in between two P type bead, and here in this case this N channel is constructed in between two N type bead. N plus and P. N plus means this the doping concentration has been very higher. Okay, that is why it is denoted by N plus sign. Now the voltage in between drain and source, which is basically defined by VDS, and the current leaving from the drain terminal is called drain current, which is denoted by ID. Next one is gate. There are two internally connected heavily doped region, impurity region, formed by diffusion technique, is basically called the gate in between PN junction. Basically a voltage VGS is applied between the gate and source terminal. This is the gate terminal, this one is the source terminal. So the potential VGS means the voltage applied in between gate and source terminal in the directions to reverse bias the PN junction. This is the PN junctions. Okay, conventional current entering the channel. This is the conventional current. Due to the migrations of charged particles, a current will flow This is called the conventional current. Entering the channel is denoted by IGE. So now what is channel? A question has come, what is channel? The region between source and drain. Source, this one is source terminal, this one is drain terminal. For P-type or N-channel MOSFET, this is source, this is drain, and for P-channel MOSFET, this one is source, this one is drain. So the region between source and drain, sandwiched between the two gates, is called channel, and the majority carriers move from source to drain through this line. Okay, this is the sandwiching length which has been created in between source and drain. Okay, that is why it is called the channel diffusion. And the current is entering through the source terminal, I told earlier, previous slide, because source terminal means this is the terminal through which majority carriers are entering. So current will flow from source to drain through this channel, through this diffused channel. And this is basically called the metallization layer, and the layer in between metal and surface, semiconductor substrate surface, is made by insulator layer, which is basically called which is basically made by SiO2 layer, silicon dioxide. Okay, this layer, similarly here in this case, this layer, silicon dioxide layer. That is why it is called IG, insulated gate bipolar junction transistors. Sorry, insulated gate field effect transistors, because the gate terminal is not directly connected with the substrate terminal. It is separated by an insulating layer which is made by SiO2 layer. Okay, now I am going to the next slide. In previous slide we have seen the basic constructions of N channel and P channel MOS. Now in this slide I want to explain the operating principle of MOSFET after biasing. So MOSFETs are basically operated in two modes. One is depletion mode, another one is enhancement mode. I talk later about enhancement mode of operations. Now I am describing the depletion mode of operations. What is depletion mode? Depletion mode means, suppose this is the MOS structure you have chosen, the substrate made by P-type and the channel obviously N-type channel, because if you want to create PN junction, obviously you have to select opposite bead respect to other. If this substrate will be N-type, then the channel will be P-type, and this is the metallurgical contact, and this is the silicon dioxide, which is a dielectric layer. So depletion means when the gate terminal is connected to the negative polarity of the battery and source terminal will be positive, and similarly the drain terminal is positive respect to source and substrate terminal. This kind of connection is called depletion mode connection. So what kind of operation basically happened inside this structure, we have to see. When the gate is made negative with respect to the substrate, gate is made negative with respect to the substrate, the gate repels some of the negative charge carriers out of the N channel, and this creates a region in the channel which is called the depletion region. Gate is negative and the substrate is p-type substrate. So what is basically happening over here, there will be some amount of repulsion, and due to this repulsion what will be happened, we found a layer which has been formed in between source and drain, which is called the depletion layer. So now that means if the width of the depletion layer is increased due to the change of the polarity, due to the variations of the external potential in gate terminal, the channel resistance is gradually increased. Why? Because we can see from the figure, the depletion layer almost covered the entire channel width. That means the channel resistance become much more higher, but the amount of flow of current which will be reduced. And this condition or this mode is basically called the depletion mode MOSFET. Here basically what is happened, too much negative gate voltage is applied, and due to this too much negative gate voltage, the channel pinched off has been occurred, like JFET. And that is why the channel resistance has been increased due to the increased of the width of the depletion layer and reduce the drain current ID. Drain current basically denoted by ID. ID reduced and channel resistance is increased. This is the basic operations of depletion type MOSFET. This is the characteristics card. This is the drain characteristics card, because we have already seen that the drain terminal is the output terminal. Why? Because the majority carriers leaves from the drain terminals and enter towards the source terminal. So this is the drain characteristics card we have plotted over here, and this one is the transfer characteristics curve. So what is drain characteristics curve? This kind of curve basically plotted in between VDS and ID in some milliampere range over here, and VDS in volt. When we have applied negative gate voltage, that means Vg is constant. Suppose I have taken Vg is equal to minus 2 volt. So in that plot we have seen that drain current is gradually, exponentially or gradually increasing if we are increase the VDS, but after a certain point we can see that it will become constant. The drain current become constant at a particular voltage, and this particular voltage for this plot, when Vg is equal to minus 2 volt, is called the pinch off point or the pinch off voltage, because here the current become saturated but the voltage is increasing along x-axis, but the current becomes saturated, and this is called the pinch off voltage. And this region is called basically, before pinch off, this region is called the ohmic region, because in this region we have seen if we increase the voltage, the current is also increased gradually. That is why this region is called ohmic region. Similarly, in case of when Vg is equal to minus 4 volt, same phenomenon is happened. Now if we operate a MOSFET in enhancement mode, in that case the polarity has been changed. That means in case of depletion mode, Vg was in minus polarity, but in case of enhancement mode the VG become positive in polarity. I will discuss later about enhancement mode. Now this is the transfer characteristics in depletion mode. This is the linear regions. If we increase the plot in reverse direction, so what will be happen? Suppose this is minus 2 volt and we are getting this point across respect to this plot which is also minus 2 volt. Now when VGS is equal to minus 4 volt, in that particular, for this particular plot we are getting a point over here. Similarly when VG is equal to 0 volt, for that case we are also getting a point over here. And now if we connected this point, then we will get this region which is called the linear region, and this characteristics features or this characteristics curve is basically called the transfer characteristics curve of MOSFET. Now I am talking about enhancement mode operations of MOSFET. So why it is called enhancement mode and what is the basic difference in between enhancement mode and depletion mode MOSFET. From this diagram we can see that in case of enhancement mode the gate terminal is made positive, but in case of depletion mode we have seen the gate terminal made negative. That means the external potential applied to the gate terminal is negative. But here in case of enhancement the gate terminal is positive. The main difference is nothing but it is so the main difference in between DMOS and EMOS. DMOS means the depletion MOS and EMOS means the enhancement MOS is that from the diagram we can see the substrate extends all the way to the silicon dioxide and no channels are doped between the source and drain. Okay, this is the basic difference in between DMOS and NMOS. No channel are doped between source and drain terminal. This channel is induced channel. Okay. Now what is the operations of this mode? The operations is the gate is positive, that means VG is equal to some positive quantity. VG is greater than 0 volt. When this condition will be satisfied, then the device will be in on state. That means VG is equal to 0 or less than 0. That means the MOSFET does not operated in enhancement mode. When VG is less than 0, that means the MOS operated in depletion mode. But when VG is greater than 0, the MOS operated in enhancement mode. That is why when VG is equal to 0 or less than 0, the MOSFET is basically called the normally off for this particular case, for enhancement case. But in case of depletion case, here VG is negative quantity, that means VG is less than 0. In that situations, when this situation is arised, then the MOS will be on state or operated on. But in case of enhancement, VG will be greater than equal to 0 volt, then device is on, otherwise it is off. When VG is equal to 0. Now I am going to the next slide. This is the characteristics card. Here I have seen that VD and this one is the ID. This is VDS. VDS means the applied voltage in between drain and source terminal. this is the drain terminal and this one is the source terminal. So the applied voltage in between drain and source terminal is denoted by VDS, and VGS is constant, same characteristics curve, but there are some difference due to the change of the polarity across the gate terminal, and VGS is nothing but the potential difference in between gate and source. So what is basically happened here, we have chosen VG is equal to positive quantity, that means VG is equal to plus 1 volt, plus 2, plus 30, plus 40, all are positive in nature, that means greater than 0 volt. So we can say this kind of operation is called enhancement mode operation, and this is the same phenomena. This is the saturation regions, or you can say the pinch off point. These are the pinch off points. Suppose for this plot, when VGS is equal to 40 volt, this point is called the pinch off point. This is called the pinch off point for this plot. This is called the pinch off. This is called the pinch off. Pinch off means the particular voltage due to which the current become constant. The drain current is become constant. This is called the pinch off condition. Now from the transfer characteristics curve of enhancement mode, we have seen that when VGS become positive in nature, then the current will flow rapidly. But when VGS is less than 0 or less than equal to 0, that means the current become very very small, IDSS, and in that case the MOSFET is operated in depletion mode. But in case of enhancement mode, obviously the output, the gate voltage will be positive in nature. That means when the VGS is made positive, and gradually we can change the, or we can vary the voltage from 1 volt, 2 volt, 20 volt, 40 volt, the drain current become increased, and we are getting different plot for drain current. Similarly, when basically what is happening, when VGS is greater than 0 volt, in that particular case, that means the VGS is positive, the drain current increase rapidly, slowly at first, then much more rapidly, and the minimum value due to which the drain current try to moves up, this is called the VGST, which is called the gate source threshold voltage. This is the minimum amount of potential through which we will getting the gate current has been started to flow. Simply, this is called the threshold voltage, which is called VGST. Now this is MOS capacitor. So what is MOS capacitor? MOS capacitor is basically made of a semiconductor. It may be silicon, it may be germanium, whatever it is, semiconductor body. Okay, and this body may be p-type substrate, may be n-type substrate, body or substrate, an insulator and a metal electrode, and this electrode is basically called gate. That means this is a capacitive effect in between gate and substrate. So this kind of configurations is called the MOS capacitor configurations. So what is basically happen when VG is equal to VG less than 0 volt or FB, flat band voltage. Case 1 is similar to VG is equal to less than 0. When VG is less than 0 volt, when VG means the gate voltage less than 0 volt, in that case what will be happened? The body or the substrate is p-type substrate. The substrate is p-type substrate. So the majority charge carriers in p-type substrates is holes. So holes are attracted towards the SiO2 layer. This is the gate terminal. The blue color represent the gate terminal, the metal terminal. The yellow color represent oxide, silicon dioxide, which is insulator. That is why it is called insulating gate, because the gate does not connect it directly with the surface or the substrate. Okay, and the green terminal is the substrate terminal. Here the chosen substrate is p-type substrate. So what will be happen when Vg less than 0? That means gate terminal is negative. So what will be happen? Holes are attracted towards the silicon dioxide layer, but they don't move across the gate terminal because SiO2 layer is insulating layer. So that is why all the holes or the positive charge particles are accumulated near the channel region. All of these blue circles are positive charge particles or holes, and they are accumulated over the channel region, and this region is denoted by the accumulation region. So from these observations we can conclude that the gate, which is a metal, which is a parallel plate, because here we can see that the negative charge particles are storing over here. Similarly, the channel, which is also acts as a second parallel plate, and silicon dioxide is a dielectric. So this kind of effect is called parallel plate capacitor effect. Now in second case, when Vg greater than 0 but Vg less than threshold voltage, so what will be happen? Vg is greater than 0. That in second case I am observing the second case. So what will be happen? Magnetic carriers attracted to the channel regions. Magnetic carriers means Vg is just above 0 volt. So in p-type substrate, the magnetic carriers are electrons, and they will be obviously attracted because the gate terminal is now positive. So positive negative attractions will be happen. So the electrons are recombines with holes at the channel region, and they leave some immobile ions, which are basically negative immobile ions. I have already shown over here, and due to this left immobile ions, what will be happened? A layer will be formed, which is called the depletion layer or the depletion region. So if the width of this region is increased, that means the effective capacitance is decreased because the distance has been increased gradually. That is why the effective capacitance decrease. So here in this diagram we have seen there are two capacitive effects. One is for oxide, which is COX, which is denoted by COX, oxide layer capacitance, and another one is C due to depletion region, CDEP, C suffix DEP. So if we calculate the total effective capacitance, that will be equal to 1 by C equal to oxide capacitance. Why it is 1 by C? Because the capacitors are connected in series. C oxide plus 1 by C depletion. This is the summations of two capacitors, oxide layer capacitance and depletion layer capacitance, and that will be the total effective capacitance. Okay. Now in third case, case number 3, this is the third case. Here I have chosen Vg is greater than Vt or Vt less than Vg. That means the gate terminals become more and more positive. So what will be happened? Initially depletion region has been formed. I have seen in earlier case. Now the gate is biased large amount of positive voltage. So what will be happen? Much more amount of minority carriers from P side attracted towards the N side. Much more amount of minority charge particles are from P side attracted towards the gate terminal, and few particles are recombined inside this bead, and due to this reason what will be happened, an inversion region or inversion layer has been formed. Okay, and the negative channel acts as a the negative charge particles acts as a channel. So when Vg is less than 0, in that case the channel confined by holes, but when Vg greater than Vt, that means the gate terminal become more and more positive. In that case the channel confined by negative particles, which are basically electrons. That is why it is called channel inversion. Now in this slide I have discussed the MOS capacitor's band structure. This is the vacuum level which I have told in PN junction. Phi m is nothing but this is the metal work functions, and phi s is the semiconductor work functions. EC is the conduction band of the semiconductor, and EV is the valence band of the semiconductor, and EFS, this is the Fermi level. EFS is the Fermi level of semiconductor, EFM is the Fermi level of metal. So this is the metal portion, this is the oxide portions, and this is the semiconductor region. So this is the connection in between metal, oxide and semiconductor. That is why it is called MOS. MOS. That is why it is called MOS, metal oxide semiconductor. This is an ideal case when the both work functions, the metal work functions and the semiconductor work functions are equal. Psi of m is equal to psi of s. Here the external potential V is equal to 0. So in that condition the Fermi level of metal and Fermi level of semiconductor both are lying in the same line. Why? Because the external potential V is equal to 0. That is why this is called the ideal MOS capacitor band structure. V is equal to 0 and phi m is equal to phi s. The metal work function is equal to semiconductor work functions, and that is why what will be happened, the Fermi level of metal and semiconductor both are lying in a same line. And why it is called flat band condition? Why it is called flat band? Because from this figure we can conclude that there is no charge particles accumulations is happening either in metal side or in semiconductor side. There is no charge particles accumulation is happening. That is why this kind of structure is ideally called flat band structure, and that is why what is happened, there is no band bending structure is not happening. That is why it is called flat band structure. Okay, or you can also say this is called the band structure of MOS capacitor is in equilibrium condition. Now in this slide I have discussed the band structure of MOS capacitor when we applied external potential, and these potentials are when V less than 0 volt, that means the metal terminal is negative inside, and another one, or the case 2 is V when V is greater than 0 volt, that means positive in sign. So in case 1, this is the diagram for case 1 when V less than 0 volt, and this is the diagram when V is greater than 0 volt. So while the metal is negative potential respect to the substrate, here the substrate has been chosen, suppose P type substrate, then what will be happen, the Fermi level moves up by the amount of charge particles and amount of applied voltage externally. For case 1 when V is less than 0. When I am moving the Fermi level up, what will be happened, I am biasing this negative with respect to the P type semiconductor, which basically means that the holes are going to be attracted, because the majority particles are holes that will be obviously attracted towards the negative terminals of the metals. This is the negative portions and this one is the positive portions. So if I am moving this level shifted up, upward directions, so what will be happen, my Fermi level is remains same, but the remains same because once I have applied the voltage, again it is in a equilibrium situations, so there will be no current flowing. So the Fermi level of the semiconductor remains same, but the other energy structure for valence and conduction band is going to increase and the band is moving upward directions. In these situations, basically what is happening, P type substrate means the majorities will be holes, so that means I have much more amounts of holes in the substrate, because now what I have done, my Fermi level which is constant is going to moving closer to the intrinsic level. This is the Fermi level which is moving closer towards the intrinsic Fermi level, and I am going to have a positive charge accumulations over the semiconductor. These semiconductor regions, what will be happen, positive charge accumulations will be happen. And same amount of negative charge accumulations also happens across the metal side. And this is basically acts as an parallel plate capacitors. Okay. Now in second case, what is happening when V is greater than 0. So V is greater than 0 means the Fermi level of the metal will be moving down, because we know potential energy is minus E into V. That is why this level is shifted downwards, because potential energy is equal to minus E V. Fermi levels and the edge of the valence band. This is the Fermi levels E of F, and the edge of the valence band is moving away from it. Hence the Fermi level of the semiconductor just moving away, and the material is getting less positive charge, and towards the less positive charge or negative charge across the semiconductor and metal. So there is less positive charge and less amount of negative charge. So this is the band bending structure of MOS capacitor in two cases, when V less than 0 volt and V greater than 0 volt. Now this is the CV characteristics curve of MOSFET. C means the capacitor, V is the voltage. Y-axis has been represented the capacitance and V-axis represent the voltage, and VTH is the threshold voltage. Now I have already told about three conditions when V less than 0, V greater than 0 and V greater than VT. So here in this plot I have seen there are three regions. One is accumulation region, second one is depletion region, and third one is inversion region. So when VG less than VG less than 0, in that situations, or you can also say VG less than flat band voltage, in that situations the effective capacitance COX is basically happening across the accumulation regions. This is the accumulation region. When the frequency is low, that in that situations, in that case, the inversion of the charged particles is almost constant. So that is why it acts as a parallel plate capacitor. Here from this plot we can conclude that here in low frequency case the amount of charged particles are remain constant. That is why it is almost equal to COX, the capacitive effect. But at high frequency case, due to the increase of depletion region, I have already discussed in previous slides, due to the increase of depletion region or the depletion region, which will be basically varied with the applied input voltage, and the substrate which have been acts as a parallel plate, the overall capacitive effect is falling down or gradually decreased, because due to the increase of depletion region or depletion layer inside the MOS, what will be happen? The total distance has been gradually increased. That means in case of parallel plate capacitor, the total capacitive effect has been increased due to this region, which is called the depletion region. That is why the overall capacitive effect is falling down in high frequency case. And this is all about the MOS capacitors in this lecture. Thank you.